This video is going to introduce you to the operation and overview of the Cen-Tech digital multimeter, or DMM for short. This video is going to focus on the Cen-Tech 61593 model and is the one that we're going to be using in this program. Again, DMM is the shortened acronym for digital multimeter, meaning that this is a digital function that measures multiple different types of signals, including frequency, diodes, resistance, and things like that. So what this is going to do is we're going to focus in specifically, like I said, on the 61593 version. So on the screen on the left is the Cen-Tech manual for this model, and on the screen on the right, this is an actual DMM that you guys will be using. Now we're going to go through some of the functionalities and the options beforehand, but again, this is just kind of the overview to get you familiar with how this tool works. So the first thing that we're going to do is figure out exactly what does this measure. So in the manual, it talks about the 11 function digital multimeter with audible continuity. So these are the functions that it can do. As we scroll down, here's a picture of our meter with the probes. As we get through this manual, we're going to get into some of the operations of this, where we have talk about the safety, the specifications of it, the setup, operation, maintenance, warranty, all that stuff. This is all again contained in the manual. When we get into the manual, there are going to be some warning symbols and some definitions of things that can happen. So please take note about these, and when you see those, please pay attention. Obviously, follow the instructions listed behind it for what's going to happen. And when in doubt, turn the system off and then proceed with the connection or the troubleshooting or whatever it may be that you're using this digital multimeter for, this DMM. Again, there's some more safety informations. I will leave that for you to go through inside your manual. As we continue to scroll down, we get down to the functionalities of this DMM. So this DMM can measure, like I said, multiple different things. And what we are looking at is we can measure diodes, we can measure continuity, we can use this section here to measure resistance. This over here is DC voltage, AC voltage. This gives us a temperature setting, which the probe comes in the manual. Please talk to your instructors about getting those probes if needed. This section down here measures transistors on a limited scale, kind of a nominal working scale, minimal voltage, minimal currents, to tell you how your transistor is working. This one section right here, this is for AC current. This section here is for DC current. This section right here is to measure capacitance of capacitors. And then this section right here is measuring frequency. Now, moving on with that, at the bottom of this, we also have some jacks and positions that we can plug in. These are female banana clips. This is where you're going to plug in your probes that go into them. And what we have is our probes are going to look like this. They look like kind of like pencils with metal tips. They're going to have long cords, and on the end of them, they're going to have these types of connections, which is the male part of the banana plug. Those will plug into these sections here, depending on which functionality we're going to need. And we'll talk about that more once we get into the operation of the DMM. So one of the things that we want to look at is in our specifications is what are the limitations of each of these settings, because we don't want to break the measuring device. If we break it, then we have to get a new one. We have to tell our bosses, our teachers that it's broke, and we just don't want to have to deal with that. So in here, this lists all the maximums for all the different types of measurements. For DC voltage, we want it to have a range of 200 millivolts, 2 volts, 20 volts, 200 volts, and 1,000 volts. And we want to have the ability to put a maximum and not exceed the maximum of 1,000 volts DC, 700 volts RMS, which is the average of a sine wave of an AC wave. So keeping that in mind, keeping this 1,000 volt DC limit is what we are after. We have our accuracy in here, how far they are. So from the 200 millivolts to the 200 volts, we're at 0.5% of our range, plus or minus 1 decade. We'll get into those a little bit better. But really, we're looking for about 0.5% of accuracy that we're after. So these are good little meters. Our AC voltage, we have different ranges. And the one thing we need to know is with AC voltage, what is our frequency range? If we exceed this frequency range for AC voltage, the DMM will actually change internally and give us faulty values. So in this case, this DMM that we have has a maximum of 40, or a minimum of 40 and a maximum of 400 hertz. So those are the absolute limits of what we can put through this thing. No more, no less. That's what we're after. Then again, we have our accuracy. We've got DC current and DC current accuracy. We're 0.8%. We have our maximum ranges. Again, we go up to 400 hertz. And this is 400 hertz is going to be fairly standard across many DMMs, not just necessarily the Cen-Tech variety, but keeping in mind what can and can't I measure. If we're measuring a circuit that's operating at 1,000 hertz, 1 kilohertz, this thing is going to lose its accuracy and we're not going to get proper measurements measuring AC currents. So be aware of that. We have resistance measurements that we can measure up to. In this case, it gives us, the different ranges, with the maximum being our 200 megohms. We've got our capacitance measurements. We can measure into the 2 nanofarad range all the way up to the 20 microfarad range. However, if we are just curious what the frequency is and we're wanting to use the DMM to determine that, this has a maximum frequency range of 20 kilohertz. So if we're just measuring frequency, it can go to 20K. If we want to come back up here and measure AC current or voltage, then we have to take into account that 400 hertz limit that we have for those frequencies, for those functions. So frequency by itself will just give us an accurate measurement up to 20K. If we want AC measurements, it has to be below 400 hertz. The temperature range that we have, this one can accurately measure from negative 20 degrees to 1,000 degrees centigrade. And we have a sampling rate of 2 to 3 times a second. This is how many times it's checking the circuit. Obviously, the more times it checks it, it averages those out. We're going to get a more consistent and more accurate number as depending on what we're doing. Now, if we're measuring DC, this 2 to 3 times per second is pretty good and it's not going to give us any problems. AC, again, that's where we get into the limitations. Where at in the waveform is this thing sampling, and that can cause problems. Here we have overload protection. This is one of the big key things that we need to have in here. We have a fast-acting 200 milliamp, 250 volt fuse. This is going to become important when we're measuring. I will show you where that is and how to change it. And there is an error in the book later on. It talks about replacing the fuse. It lists it as a 2 amp fuse, 250 volts. Do not put a 2 amp fuse into this DMM. If you put a 2 amp fuse in there, you will break something internally. This is designed to protect itself so it cannot exceed levels that can cause damage internally. So just remember 200 milliamp fuse. And it's also listed on the DMM. So if you look right here, and I'll try to bring this into focus a little bit more. So underneath this camera right here, maybe, there's a little note on there that says 200 milliamps max. So again, reminding you of how big the fuse is. If you forget that, or if it gets worn off, you can always scroll back up here to the picture. And right here in the center of this, you can see the warning. It says, again, 200 milliamps for max on that fused connection. Again, I'll talk about where that comes into play and how we change that. So we're going to come back down here to, scroll past it, to our limitations. We have an LCD display, and we've got a 9-volt battery. It is important that we maintain this battery. If this battery gets too low, we're going to see some delayed responses from our DMM. We're going to see inaccurate measurements. So if we're starting to see things going awry with this, we just want to make sure we check that battery. That could be one of our problems. Or if our DMM just doesn't even turn on. So be aware of that. So again, going through the manual, here's going through how to set up your tool. We're going to talk about this depending on what you're after. Your functionalities, which functions I want to do. Basically, this is where your red lead connection goes. Again, it's going to go into one of these spots over here. So your red lead will plug into one spot, your black lead will plug into the other. And most of them, the black will stay right there in the common, and the red one is the one that moves around to the other 3, depending on which functionality and which function you're trying to accomplish with. Here's some more additional precautions that you want to take. Make sure you don't measure or don't exceed those limits. There's some general operating instructions. Basically, the biggest thing about these is starting with the highest value if you're unsure and stepping it down into what the value is. The tool will actually protect itself better if you go to a higher level, and then if you need to go smaller, it's better. If you start from too small of a level, depending on what your input is, you could actually burn something up internally because it's expecting a smaller value and therefore going through a different part of the circuit. So always start high and then move down low if you're unsure or not sure where to go. This will go through and talk about how to take some of these operational measurements. There's DC voltage, AC current, DC current, and it goes through the whole list. We'll go through a couple of these specifically and show you what's going on. And then get down in here to the end of it. Here's some cleaning, maintenance, and lubrication of it. And then down here, this is your battery and fuse replacement. So if you do see that symbol on there, it means your battery is low and you need to replace it. So this walks you through how to do it. Right here on step 5, this is where that mistake is. In here it says it has a 9-volt battery or a fuse, that's what the F stands for a 2 amp, 250 volt quick acting fuse. This should be a 0.2 amp, 250 volt. So in this part of the manual, this is incorrect because everywhere else it's stamped with the 200 milliamp, which is 0.2 amps. So just be aware that that is a mistake. We'll go through that operation, and here there's more information about your warranty and then the end of the manual. So that's kind of the end of the overview of how this DMM is supposed to work and some of the options that we have with it. The next part of this video is going to be where we start getting into the specific functions, and we'll talk about some of the more common ones that we're going to use, and how to use and use this meter to the best of your ability. This portion is going to be for the operational aspects of this DMM. So the first thing we're going to look at is with our DMM, what comes with it, where everything's at. So again, we have our probes, a black and a red one to keep directionality and polarity correct. We have the banana plug pins, the male side. The female side are the ones down here, and those, the plugs, the connection point. And up here at the top, this is our power button, this is our hold button, this is our function selection dial. So how this works is when we're going to come up to do a measurement, we first have to turn the DMM on. So on here it's listed, if you push it in, it's turned on, if it's out, it's off. Right now it's in the out position, so it's off. We push this guy in, it's going to go through its startup routine and then go to this screen. Right now we're measuring continuity is where it's set, continuity and diode checking, and it's reading at a -1 point nothing, there's no information in there, there's a music note right here. So what this is telling me is in its startup mode, it is not detecting any continuity, which means there's no connection because there's nothing in these two plugs. There's nothing connecting where the meter is trying to read from. So this is telling me that I have an open. There's nothing going on. There's no electricity flowing from one point to the other. And we'll talk a little bit more about that here in a second. So first thing is, if this thing doesn't turn on or this power button doesn't work, the first thing I'm going to go after is the battery just to double check. So you want to turn this into the off position so this thing is lifted up, and this one has a case on it. You're going to grab the case, either the top or the bottom, you're going to push it and peel it away, and then pop your meter out so the case is now out of it. You can set that off to the side. Now that we have here, when we flip it over, we can look. Up here is our battery compartment. We have a screw holding it on. We've got 2 screws down here. So for a battery change, that is fairly simple. What we're going to do is simply get a Phillips screwdriver, and we're going to take this screw out here. So we're going to do that. It'll come out. We set that off to the side so we don't lose it. We pop our battery cover off, and there's our battery. So we can take this, use our screwdriver to kind of pull this out a little bit. Use your fingers. Smack it around a little bit as needed. Usually if you smack it on your hand real quick, it pops the battery out. So we want to be careful of those wires, make sure we don't pull too hard. Here is where the battery is going to connect in. The positive is going to be off of our red wire. The negative is going to be off of the black wire. Now when we pop this off, we can also see here that the positive side of the battery is the little nub side. The negative is this crown. So same connection points, we've got a nub and a crown. We want to put those so they match up with the battery. So we take those, we reconnect those back in. There is, how to change your battery. Well, now let's say you turn it on and you did something else. Your fuse, and you blew a fuse, your fuse is located in with the same steps to get to it. So we need to take that screw out to get the battery cover, which accesses us to the battery compartment. And then we have it also hidden underneath here is 2 more screws. This one's missing one, and that's okay. Yours will probably have it to start with, and or you may lose one in the process. So it's not absolutely necessary that we have all those screws. It's nice to have them, but as long as we have 2 or 3 of them, the back's going to stay on and it'll work just fine. So this one's missing a screw, this one has a screw. If we flip it around on this back end, we've also got a screw here, and we've got a screw here. So there's 4 more screws to take off. If we're going after the fuse, we're going to take these screws off, again using our small Phillips screwdriver. We'll loosen that one. We will loosen that one. Okay, and then this back cover is going to just simply, we kind of pry it apart, and it's going to pop off. Now, when we open it, if you notice that we have that wire from our battery is now coming inside from here down into that board. You do not want to pull on that connection, you don't want to do anything. One thing you can do is you can have the battery pop out and disconnect it, set that off to the side, and now these are in 2 separate pieces. You can set one down without having to ruin it. And I would suggest removing the battery anytime you're going to mess around with this fuse, just so you don't accidentally short something. Now, inside this, as we look down, right down here is our fuse. This is what's going to be another one of our culprits for problems. To remove this fuse, we just simply take a screwdriver, get it underneath of it, or a fuse holder, fuse remover, and pop that fuse out. Now, on here it's kind of hard to see, but around the edge of the fuse, there is, on one of the sides, right here, so it's going to be really hard to see in this camera, but right across this lip, it actually tells us the size of fuse this is. So this one says it is a 0.2 amp, 250 volt fuse. So it's really, really hard to see in this camera, so unfortunately I just have to take my word for it that that's what it is. If we look inside, if I can get this to focus, maybe, not really. Inside you can look through the fuse. There's a little filament that runs the length from side to side. If you can see that filament, it's usually good, but we also can check it using a continuity meter. When we use the continuity meter, it should register as 0. The cool things about this fuse is used to measure current. And if we exceed the current limit, we pop this fuse, but the rest of the meter actually works just fine. So I'll show that to you. So we've got the fuse taken out. We're going to set that off to the side. We're going to take our cover. We're going to put the battery compartment back through like this and just kind of put it together. We're going to hold on to it. I'm not going to put any screws. Take my battery, match up the sides again, so we should have, it'll only fit one way. Pop that back in. And now, when we flip it over, we can turn this on, and we set this little thing to continuity. So now, when we're trying to measure continuity, this is under our resistance, the ohms measurement. So if we come down here to the bottom of the meter, we have our common, and we have this symbol over here for ohms, the resistance. So this is telling me my red one needs to go here into the red, and my black one stays here in the common. Also in the instructions, it'll tell us when we're measuring continuity that if we want to measure continuity again, right here on our meters, continuity, we're going to put the red lead into the voltage or ohms, or the voltage ohms hertz, depending on the model. This one is the voltage ohm hertz combination. And then again, it tells us the maximum input limits that we have is 200 volts DC. If we're measuring ohms or continuity, the system should be off before we take any measurements. So we got this powered on. So I'm going to take my probes. I'm going to take the black one, put it in my common. I'm going to take the red one, put it into my red one, which says volts, ohms, and hertz. And then I'm going to set this down. And my fuse, which is right here, I'm going to take my two measurements. I'm going to tip this up some more so we can see the screen. So my fuse, we're going to take our probes and we're going to touch them to the edge of each of the fuse, metal to metal, metal to metal. So when we do that, our DMM is going to read it, and if you can hear it, it started chirping. Well, what that chirp means, and if you've noticed the numbers, it starts reading a very, very small number. 0.000001, something like that. And it's making that noise. So what that is telling me is continuity-wise, it's the same as if I took these two probes and touched them together. It's telling me by that tone that those are connected together. Now, if they're supposed to be connected together or not, that's what my job as a technician is to figure out. Should it be touching? Should it not be touching? So when I'm checking my fuse, this fuse should read as a continuous connection, and meaning that it is not blown, that it's still a good fuse. So it is. If we don't get that noise and this value here does not go to 0, that means that this fuse is blown. That little filament that's inside of it has exceeded the current and exploded. So there's no longer a connection in there. And if that's the case, we need to take this out and replace it with the same type of fuse and then put it back in as we're going. So I'll show you how to reinstall the fuse once we're done. So again, we'll take our probes out because it's just easier to work with them. Turn this guy off, flip them over. If these screws here and here in the four corners were not already done up, we'd re-loosen them, take it apart, and do these same steps. But since I never tighten these back down, I can just open this up, being careful of my battery connection, take my fuse, and in these two little prongs that are standing up right here and here, I can take my fuse, pop it back into place until it connects, make sure that the metal fuse holder is touching the fuse, flip this around, maybe get a better view. So those little metal fuse holders on the side, make sure those are connecting with the fuse that's in there, and we now have continuity again. Then to reassemble, we take our connections, or our covers, we put them back together, and since I'm done with this, then I'm going to tighten the screws back down, put my other screw in the opposite corner just to give it some strength. My battery's reconnected, everything's working. I'm going to take my cover, put my cover back on, take the little screw, put it back there, not lose the screw. Tighten that one back down, and then I can take my cover, slip it back in under the lip, push it down, and then just pop this back in. The covers you may have, they may have a little bit of a stand. This thing will pop open, and then you can kind of set it up like this, so that way you can work in. This screen can tip forward, and it can adjust however you need to view it. This one doesn't have that kickstand, and I'm going to leave that screen flat so we can look at everything back again under the camera. So that's the basic operation of how to check for your battery, how to check for your fuse, how to replace your fuse, and things like that. So the next part we're going to go through is some of the functionality. So again, with the resistance, we're going to be measuring different values. So up here on our selection dial has a little arrow. We're going to twist and turn that arrow to give us the direction of and point to whichever function I want to go after. Do I want to measure resistance? Do I want to measure DC voltage, AC voltage, temperature? If I want to measure transistors, AC current, DC current, capacitance, and frequency. So in this demonstration, we're just going to show you with resistance. So here I have some resistors set up on a board. These could be the same as what you're looking at, or you could have some that you're pulling out of your workbench, your drawer, your parts that are supplied, whatever it is that you want to measure. So what we're going to do is we're going to look at these different measurements and we're going to figure out which ones do I need to do, how do I set this meter up. So I want to measure resistance, but there's a bunch of different options. So I have to kind of first off determine what resistance am I going to measure. So I'm going to measure this resistor right here, this fourth one down. So it is a brown, red, red, silver. Now, according to our color code, this is going to be a 1.2 kilo ohm resistance or 1200 ohms. So if I look at my dial, what I have here is a 200, 2K, 20K, 200K, 2 meg, and 20 meg. So I know that I'm going to be measuring a value that is 1.2K according to the color code. So I'm going to look at my dial. 1.2K is bigger than 200, so I don't want to measure that one. And the 2K is the next closest one over it. So I'm going to adjust my dial to the 2K setting to tell me what this resistance is. So the max it'll measure is 2K on this range. If it's bigger, it'll go over, and I'll show you how that works. Then, since I'm measuring resistance, I'm going to look back at either my manual, which is still on the screen next to me, or down here at the bottom, I'm measuring resistance. So my red probe is going to go into the slot for resistance, and my black probe is going to go into my common. 99 times out of 1,000, 99 times out of 100, sorry, this black one is not going to move. With this specific DMM, it really should never move. We're always going to have it in one spot. We're just going to change the red probe to the different options. So now I've got volts, ohms, and hertz over here. It's kind of hard to see. I've got my common connected. Now I've got my probes are now ready to go. They're connected to my circuit, or sorry, to my DMM, which now I can then go measure these values. So one of the key things too is when you're going to go measure resistance, you need to make sure that that component is isolated from the power source. Turn it off, disconnect one side of it is all it's needed, and then you can measure the resistance. If you have an entire circuit connected up and you go to measure resistance, you're going to measure the entire circuit from wherever the point of view is where you put your probes. If it's disconnected from the circuit on one side, that means it'll only measure that point to that point. So just be aware of that. So now I'm going to go and measure resistance. Now resistors do not have a polarity. It doesn't matter if I measure them like this or if I measure them like this. There are some components that are polar sensitive, so they need to be measured in the proper way. So in this one, I'm going to measure this fourth resistor. I'm going to touch down on the metal contact on the one side, touch down across the metal contact on the other side. The DMM is going to do its thing. It's going to measure how much resistance it is and display it on the screen. So in this case, it's supposed to be a 1.2 kilo ohm resistor, and I'm measuring 1.192, and then up at the very top you can see it says kilo ohms. I don't know if you saw that, but as soon as I went to go point where that value was, it disappeared because I broke contact with whatever it was I'm measuring. So one of the cool features that we have, and if we kind of do this with one hand, we can hold the probes, measure our resistance, and we can come up here to this hold button, push the hold button, which basically stores this into memory, and now I can take my probe and remove it, and then when I'm going to go and write down my notes of whatever it is, now this is going to remember what that value was even though it's not connected up. So a cool little feature with this hold button is when you hit it, it holds it on the screen, so then you can disconnect your hands, write it down, do whatever you need to do in a safe manner. So then I can take that value, write it down as a 1.19 kilo ohm resistor, and move forward. Well, now that's great if we know what the color code is. There may be a time where I'm trying to measure a resistance and I don't know what the value is. So I'm going to make sure that this hold button is off and it's registering as a 1, which in this idea represents infinite amount of resistance. So between these two probes, it's just air. It's really, really a lot, but really it's not necessarily infinite. There is a value, but right now I'm only measuring at 2,000 or 2 kilo ohms. So anything over 2K, it's going to register as an open. So with this board, if I go down and look, I know these resistors, as I go farther down on here, these ones are going to be fairly large compared to everything else. So as I'm measuring them, this very first one I'm going to measure, it's going to hopefully give me a value. There we go. So this one's going to register at 0.001 or 000 kiloohms, which is really, really small. So in this case, when I'm measuring it and I'm looking at that value, I'm reading 0 ohms. I don't necessarily think that this resistor is a 0 ohm resistor because it has a color code on it. Okay, so I'm too high of a scale. I'm going to drop to 200. So now my 200 is the max. I'm going to measure this value, and now it's going to tell me we're measuring at 1.2 ohms. Very, very small. And it's going to bounce around because it's such a small value. I can also turn it one step farther down to this continuity, and this continuity, it's going to screech, but it's going to give me a measurement. It's struggling to figure out what it is. It's a small enough resistance that it considers it's an open, it considers it a short between those points. So that one didn't really help me. So my 200 is going to give me my best option. 1.2 and kind of where it stabilizes in. So 1.0, 1.1, maybe 0.9, so I'd call that probably 1 ohm, which that's where this one's supposed to be. It's supposed to be very, very small. Now, one of the limitations that we have is nothing has 0 ohms of resistance, as much as we want it to. There's going to be some. So if we take just our probes and we connect them together on the 200 ohm set point, just by themselves with nothing else added on, they're going to settle in at a 0.3 ohms of resistance. 0.2, 0.3, somewhere in there. So that means just that connection alone with nothing else there is adding 0.2 ohms of resistance. So if we come back and measure this little teeny tiny value, we are getting 1.2 or something very, very small. And depending on how we measure it, it's where we're going to be after. So we're at 0.9. So if this thing was measuring 0.9, these were measuring 0.2, that means just the probes alone is adding 0.2 of resistance. So in that very small value, we're actually reading 0.7. We have to subtract out whatever that resistance of our probes are. So for very, very small measurements, that kind of poses a problem. That 0.2 ohms is a big deal measuring that teeny tiny value. When we get to this 1K, or this 1.2K, the one that we measured, so we're measuring 1.2K, we still are set on the 200 ohms, which means it's too big. Come back up here, move it up a level to the 2K. Now I get back to my 1.19. 0.2 is nothing compared to what this 1.2 is. So just be aware of that, that's one of the limitations. On very, very small values, your probes themselves are going to affect your circuit. So now if I go through here and measure, like I did earlier, I was at 200 ohms, I measured this 1.2K, and it read a 1, meaning I was too large for that setting. So I bumped it up to 2K, now I can get a measurement. So we're going to go down 1. So this measurement is saying that I am reading overloaded over 2K. That's what the 1 point, no nothing after it is saying it's too much. So if I bump this up to 20K, take a measurement, hey, there we go, I got a number, 4.07K. So those are my values and my limitations. Now, remember in the instructions when we were talking about the overview, if we don't know what the value is, we want to start high and walk it down until we get a value that is, close to the maximum or things like that. We do that for 2 reasons. Number 1 is so that we can get an accurate reading on it. If we have too high of a scale or too small of a scale, the accuracy of what we're trying to measure is going to change with it. So that's the first reason, is our accuracy. The second reason that we want to make sure we start high and move down is depending on what function and what setting you're on, you can actually cause problems and blow up internal parts of your DMM if it's at too low of a range. Now resistance is not that big of a deal. You can start low and go high and kind of have a little bit of leeway with it. Once you start getting into the voltages and currents and things like that, then you start running into problems. If you're measuring for 20 milliamps and you're getting 40, double the amount of current it can handle, you can actually burn up components inside of it because it's not designed to handle twice as much current as what you're putting through it. So again, resistance, you can get away with it as far as like going from a too low value and then moving it up. But everything else, if it's an unknown value, you want to start in the highest position and then step it down. So we'll do that for the resistance. So we're going to step this all the way up to the 20 meg reading. So that 20 meg reading, and we'll go back to our one that we know, which is the 1.2, the 1.19, the 1.2K. So if we measure it, it's going to give us all zeros, meaning that it is off the scale for what it can measure. And if you think about it, 20 meg is how many times bigger than 1.2 kiloohms? Well, for one, it's at least 1,000 times difference because we're going up from kilo to meg, which is 10 to the third to 10 to the sixth, so 1,000 times bigger. If we look at our screen, we are showing in decimal form. The first one, the first digit is tenths. The second one is hundredths. We're already in the thousands because we're 1,000 times bigger, so we need one digit past there and we're not even getting that. So right now we are reading way too high for the value. So I'll hold those on there and I'll use my hand. So now 20 meg is too large, we're not seeing anything. So I'm going to go down to 2 meg. Okay, that gave me an extra decimal, so it moved my decimal point over. I'm still not fully reading it. Okay, I'm going to go down to 200K. Oh look, now I'm starting to get a measurement, but now I only have 1.1 kiloohms versus megohms. Okay, so let's go to 20K. That gives me my 1.18, so we're getting closer. And if I go to my 2K, that gives me my 1.19 with my last digits. So we can kind of sneak it in. And then if we're at 2K, we know that we're reading 1.1K, 1.2K, the maximum is 2K. We're probably pretty good and we don't need to drop down another level. Biggest thing to consider is just make sure that you're not dropping down too far and that you're not going too fast. All right, that's going to take care of this first set of measurements, but this at least gives you an idea of how to use the basic functions of the DMM using your continuity and using your resistance measurements. We are now going to measure the voltage of a simple circuit. Here I have a simple circuit that's connected up to a 5-volt power supply. That 5-volt power supply has a positive connected in on the red side, and the negative side is connected up here to the black. Now, when we go to measure voltage, we need to make sure that we have our DMM set to the proper range. On our dial, with it turned on, we're going to look and we're going to see what voltage am I going to measure the most amount of. And in this case, as I said earlier, it's going to be a 5-volt signal, meaning I'm going to set my DMM to this 20 volt range, as 200 millivolts and 2 volts will be too small to get a proper measurement of the 5 volts that I could potentially have across my entire circuit. Now, with this circuit being only one component, that whole 5 volts is going to drop across the entire component. And in a moment, I will add more components to it and we will measure the voltage drops against each of those individually. So, first thing we're going to do is we're going to energize our circuit, and then we're going to take our probes. We are going to take the red is going to match with the positive polarity, the black is going to measure with the black or the negative part of the polarity. So I just need to match the colors. Here I am mismatched across my colors, so I need to flip. Red will always be the more positive side, black will always be the more negative side. And we just kind of keep that going with the normal conventions when we're building circuits, testing circuits, things like that. If we end up using different color of wires or different colors for that coming in, we just have to be aware what's positive, what's negative, and then when it comes to it, the black part the red part, we're going to measure the more positive side, and the black we're going to measure the more negative side. So now with my DMM turned on, so it's waiting for a signal, My probes are plugged into the two spaces down here, my black one going into the common, and my red one going into the one marked for voltage, voltage, resistance, and frequency. My measurement knob, my selection knob has been selected to DC volts, and I am selecting 20 volts again because that my exceeds my voltage that I have coming into my circuit, which is only 5. I then go to measure my components by putting my two probes in parallel with my desired component, meaning they're connected to both sides of it. So my red goes to the red side, my black makes contact with the black side. And as we can see, the DMM is now registering that I have 5 volts across this one component. This is about as simple as we can get as far as circuits, one voltage source, one supply. Now, if I would have taken my probes and if I would have swapped the polarities, if I would have just grabbed them and picked them up in this order, and I connected my negative probe to my more positive part of my circuit, and my red probe, which is positive, to the more negative part of my circuit, when I make contact, what I get is a negative 5 volts. So as we can see, hold these here, and I'll hit the hold button, so that way I don't have to balance. Taking this off, I'm no longer measuring no longer measuring voltage. There's still voltage is applied to my system. I have just held what my DMM was reading. So here it'll tell you the hold. So I was reading negative voltage. What that means is my electrons are moving opposite in the direction that my probes think that they are. My probes are predetermined to have the current, or the electrons, which is the current, flowing from one side to the other. And because I have reversed the direction of travel through those, the meter is expecting current to flow one way, but I am measuring it going the other way. So therefore we get a negative voltage. And that really is the biggest thing about measuring these voltages, is it's going to be positive or negative as long as I'm measuring it correctly. The electrons are going to flow through my negative, up the negative side of my probe, through my component, and back out my positive, because the electrons is what's moving. So in here, I have electrons which are inherently negative are coming to this side, and I have a buildup across the resistor, making this side more negative and this side more positive. So when I go to measure it, my red probe is expecting positive, my black probe is expecting negative, and therefore we get the problem of the negative voltages coming into place. So be aware that when you're doing measurements, make sure that you are putting your probes in the proper order, depending on how the current is going to flow through the circuit, or however you've been told to measure them in the wiring diagram and the schematics, because that can change depending on what is being asked. Now, one other thing, hopefully that you've noticed by now, is that my DMM has shut off. Right now, I didn't push any buttons. The image on the screen just disappeared. I was holding that voltage. Well, what's going on? What happens is this DMM has gone into a power save mode. If it doesn't get used for so long, or if it just sits idle, especially in one of these sections where it's trying to actively measure, if it doesn't get a signal for a while, it's going to just turn off, and then we have to do some steps for that. It's really easy to fix. We just come over here, turn it off, turn it back on. And because it came up in some weird numbers as it was measuring, my hold button was still pressed, so it just grabbed the first value that it saw and held it. So that's kind of its default startup value. If we release the hold, it goes back to 0, and now we can go back to measure normally. And I'm back to getting my 5 volts. So very, very simple, very, very easy when it's one component in one circuit with one power supply. But generally, we don't have power supplies or circuits or things like that that are only connected to one component. There's multiples. So this is just a good way to be able to see what's going on. Now I am working on a circuit that has 3 components. I've got one resistor here, one resistor here, and one resistor here across the bottom. All 3 of these are connected together in series, which means my applied voltage is going to split up between the 3 of them. So now, as I power up my circuit and engage it, I can measure my total voltage again. Again, matching to my polarities, with my red being my more positive, my black being my more negative. So I'm going to measure across the input of my circuit. So measuring across from the black to red on my input. Again, I'm measuring the 5 volts that I had to start with. So now what I can do is I can individually measure each one of these components' voltage drops by still measuring in parallel with the circuit live. So to measure this resistor right here, my black one is going to make contact with its connection point, and I'm going to hit the connection point on the other side of the resistor. And I get 1.67, 1.68 volts. Now, as I was recording this, where it's bouncing back and forth between 6.7 and 6.8, I would probably extrapolate that to be 1.675, where it keeps bouncing back and forth about half the time, maybe a little bit higher. So that resistor is dropping 1.68 volts. Moving on to the second resistor, my red goes to the more positive side of my circuit, connected to the one leg. My negative goes to the other one, and here I'm measuring 1.64, 1.63 volts. This one's solidly at 1.64. My last one, I'm going to measure with red on most positive, black on most negative, and I get another 1.67 solid voltage. All 3 of those should add up together to give me my 5. Now that I have a more complicated circuit, I can still go back and measure some of my values as far as resistance goes that I did previously. Part of the steps that I have to do on this is I have to go back and think, what do I need to do to make resistance measurements? Now before, when we were doing just a single resistor, it was really easy. But as I explained before, when we're doing resistance, we have to isolate the different components and measure them all. So if I was looking at this circuit and I wanted to measure the entire circuit resistance, everything that was connected together, the first thing that I have to do is make sure that my power is turned off. So I've turned my power off to my supply, and now I have to disconnect, I have to isolate what I'm trying to measure from the rest of the circuit. So in this case, I don't want to measure what my source is doing, so I'm going to disconnect one side of my source. That's all that is required. On my DMM, I'm going to adjust my knob to measure the maximum amount of resistance. Now, I'm not sure exactly what my resistance is, so I'm going to start by adjusting this to 200K. So first thing goes, I'm going to take my probes and I'm going to touch them to one side of my series circuit and touch it to the other side of my series circuit. First thing that I get is I got about 2.9 kiloohms being registered. So to make this a little bit more accurate, I'm going to adjust this down one step to go to 20K because I was reading 2.9, but that's larger than this 2K setting. So I have to go to the next highest, the very next step highest, and barely in that range, so I'm not going over. And I'm going to go to the 20K, and then I'm going to touch my 2 probes. So to get a little bit more accurate, I've got 2.97 kiloohms in my circuit. 2.97, 2.98. All right, so now if I wanted to take that farther and measure each one of these individual resistors, again, if I want to look at each one separately, I have to isolate it. With this power supply already disconnected from here, this is already an isolated circuit or an open circuit. There's no paths for current to travel from here to here. So in this instance, I can measure anywhere I want because I'm not going to be connected. If I measure directly across these 2 components, I'm going to get 1.99 kiloohms, so 990 ohms across that guy. And again, I can do that because there's nothing over on this side to be connected to link me back to here. This resistor over here, measured by itself, is going to give me 0.97. And from here to here, for my top resistor, I get 0.99. So taking all those into account and using Ohm's law, we can go through and calculate what each of those voltages are supposed to be. Now the tricky thing is, if I don't isolate it, so let's say I didn't take off my ground plug from my power supply. When I go to measure this, now if I leave the circuit as it is, I'm going to measure from this point, starting here, going through the circuit, into this wire, through the wire, into the power supply, through whatever components are there, and then back out. So if I come here and measure my total resistance, which was 2.97K, and measure across this, now, because of the power supply is physically connected to it, I'm getting 2.48K. So I've changed it, and we can see that. So there's 2.48. I will isolate my resistance by disconnecting it from the source, and it goes back up to where it is at 2.98. So what happens is we're actually putting more resistance in parallel if we leave our source connected, and it has sometimes a large effect on our circuit depending on what we're measuring. Now, if it was thousands of ohms instead, tens of thousands of ohms instead of just a simple 2,000 ohm circuit, we might see a bigger difference. If it's smaller, we might see another difference. It just depends on what internally is going through the power supply underneath this board. So we have to keep that in mind. Always isolate when we're measuring resistance, voltage, and I'll turn this back on again. I'm going to move my adjustments to my 20 volts. And in this case, I'm going to switch it down to the 2 volt because I know each one of my measurements was not more than 2 volts. So I can get a little bit more accuracy out of this thing. It's nice when you know what those values are supposed to be, but not necessarily we can split it up. The 20 volt will be just fine. So here, when I go to measure it, and now I'm getting a negative 1.683 volts. Well, wait a minute. Before, I got a positive 1.68 volts. Why am I getting negative now? Well, again, if you look, my probes have reversed. My positive probe is now touching the more negative portion of my circuit, and my negative probe is touching the more positive part of that component. So therefore, the current is flowing backwards to what my DMM wants to see it, and therefore throws it up as a negative sign, which, depending on how you're being told to measure the devices, could be what is wanted or desired. If you're not told one way or the other, measure it to how the current's going to flow through it and how the polarity gets charged to the components. Basic rule of thumb on that one. Now, the final thing that we want to measure in this circuit is going to be current. So voltage, current, and resistance are going to be the primary functions and the primary things that we're looking at when we're utilizing this DMM. Most of what we're going to be after is going to fall into those areas. We will sometimes get into capacitance measurements, transistor measurements, things like that. But like I said, primarily what we're going to be using this DMM for is going to be voltage, current, and resistance. So now what we have to do with current measurements is current is a little bit different. We have to first set up the meter in such a way to measure the current correctly with the settings that we have. So anytime we're going to go to measure current, I want to shut off the power to my supply first. Make sure my circuit is dead because it's going to involve messing with the circuit and then putting our meter in place. So my circuit is turned off, and now I come over to my meter, my DMM. On here, my red wire is connected to this probe spot right here, the port, that says voltage, resistance, and frequency. I'm not after measuring those, I want to measure current. So if I look down at the bottom, over here on this one says milliamps, and over here says 20 amps. So what we have is we have two options. I can read the milliamps here, and I can read up to 20 amps here. Now keeping in mind, we have that 200 milliamp fuse limitation. If we exceed 200, the fuse is going to pop and this is going to stop working. So we've already checked the fuse, it should be good. So what we want to do is move the red probe from the voltage port, and we're going to move it over to the fused milliamp port. So we'll plop that in there. This yellow one over here, this is unfused, meaning that there is no fuse to pop, but we can only go up to 20 amps. If we exceed 20 amps, we're probably going to break something inside of this circuit. And you just saw my meter turned off again, so we're going to turn it off, turn it back on, get it out of its power save mode. So now I have my meter hooked up in the proper method, my common port, my milliamp port, And now I'm going to take my dial and I'm going to adjust it down to DC amps in this bottom corner. Down here, I have 2 milliamps, 20 milliamps, 200 milliamps, and my 20 amp rating. So if I do a little bit of quick math, grab a sheet of paper. And get my calculator going. So what I'm going to have here is I got to do a little bit of math. I know that I had 5 volts in my system. I also know I had 2.97 kiloohms in my circuit. So because I had that much the resistance and that much voltage, I can then solve for the maximum amount of current in this system. So my current is going to be my voltage divided by resistance. So I take 5 volts divided by 2.97 kiloohms, and that's going to give me how much current is going through this list. So I'll bring up my calculator, and I'm going to go 5 volts divided by 2970, which is 2.97K, hit equals, and that tells me I'm going to have 0.001683 amps, which is also 1.683 milliamps. So knowing that I should have 1.683 milliamps at most in my circuit means that I'm well within the tolerance of my DMM, and I can safely measure this without having any issues. So that's the number we should be expecting to see. So the way that we measure current is a little bit different. It involves a few more steps. First step that we do, turn off our circuit. So I've turned off the power to my circuit, and that's right here. The next step is I have to break the circuit after the component of where I want to measure. So in this case, if I want to measure total current, my total current is going to be what's coming into the system or coming out of the system from here. Also with a series circuit, it can be anywhere in here, but we're just going to kind of stick to our generals. So I've got current coming in, current coming out is where I want to look. So I'm going to disconnect where my current comes out. Then I'm going to take my meter and I'm going to connect into the point where I just disconnected from. So where this alligator clip was, I'm going to put my probe on there. I'm then going to take the other probe, and that's going to connect into what I just disconnected, the part I just took off. So now the current is going to flow. The electrons come up out of my negative, through my probe, into my meter. It's going to go through the meter, it's going to calculate it, then that current's going to come out of my meter, and then through this probe, go back into the circuit, and then through the rest of my circuit. So now, I'm going to look down at my dial. I was calculating for 1.683 milliamps, so I can turn that to my smallest setting, which is 2 milliamps. So I've got 2 milliamps, 20, and 200 milliamps. We're going for the 2 because that's bigger than what I'm expecting. And if we were worried or if we were really close to the line, we could bump it up one level to be safe. So we'll do that. So I'm now at 20 milliamps. I'm going to measure my circuit. I'm on, I have a display, and I'm going to turn the power on to my power supply. So I turn it on, and now I read 1.67 milliamps. Now, verifying that I have less than the 20, I'm going to turn my power off, adjust my range, turn my power back on. So now I get down to the 1.629, which is close to what I measured with 1.684. So we're off a little bit. Again, this meter's going to cause some changes in that a little bit as far as the voltage goes, or the current goes, because this internally does have some resistance. It's going to add to the from the circuit, and it's going to slow it down. But generally, we're not going to have too much of an issue with this. So there's my current. 1.63 milliamps is my total current. Now, if I wanted to look specifically at a component, I'm going to shut my circuit off. I'm going to disconnect it. I'm Make sure we're dead. We should be reading 0. I'm going to take my meter, disconnect it, and I'm going to put it back to where my circuit was. Now let's say I wanted to see the current coming out of this resistor. So what I'm going to do is where this resistor ends, I'm going to disconnect it from the circuit, move them over there. So now I've got a gap in between these two spots. My probe is going to go here, and again it's following the polarity that the current induces. My negative is going to go right here and connect onto the leg of where I left it off. I'll kind of hold those into place. My DMM is still set up into the proper setting, and then I'm going to turn the power back on. So now I'm measuring the current coming out of this component and then going into this component. So depending on if you're doing series or parallel, just keep that in mind. Find the component you want to measure, disconnect that component from the circuit, connect one side of your meter to what component you just took out, following the polarity conventions, and then you're going to take the other spot and connect it to the component that you disconnected. So that way your meter is now taking that position instead of just having a piece of wire connecting those two. It is now the piece of wire measuring it. And then I can go through and measure. One thing I would also avoid to do is when you're using the Cen-Tech meter is I would not want to disconnect or disengage your circuit or your probes from your circuit while it is on. When you do that, you can have a current spike, and if that current spike's too high, it's going to blow your fuse. If you blow your fuse, now you have to go get a new one and get it replaced, and that takes time and money. And right now, the 200 milliamp fuses are about 50 cents a piece. So the more you blow of those, the more fuses you have to use, the more money you're going to spend, things like that. So always remember, turn the power off before you go to make an adjustment with your current, and that's even including changing your ranges. Some of the problems you can have is when you disconnect or you change this range, you're actually going to force some of that current up through the meter, which could potentially burn it out. Also, depending on how your circuit is connected, that could be a problem as you're disconnecting or changing the settings on your meter and things like that. So hopefully, as you've been watching these videos, you can now see the basics of how to use your multimeter, including measuring resistance, measuring current, and measuring voltage. What settings do you have to have, things to keep aware of, and stuff like that.